Bismillahirrahmanirrahim. Electromagnetic field theory, and today our topic is the Stokes theorem, and then we will study its application. Okay, so and the magnetic force. So let's start with the Stokes theorem. Okay, so according to this theorem, current enclosed by the closed path is equal to the surface integral of the curl of the magnetic field intensity. Mathematically, I enclosed is equal to, this is the surface integral of the closed path, okay, and this is the curl of a vector. Which vector? Magnetic field intensity. So the curl of the magnetic field intensity. Okay, so the surface integral of the curl of the magnetic field intensity is equal to the current enclosed by the closed path. Okay, so uh, according to the Ampere circuit law, we have studied that I enclosed is equal to the surface integral, the line integral of H dot dl. Okay, I enclosed is equal to the line integral of the H dot dl. And now in the Stokes theorem, I enclosed is equal to the surface integral of the curl of the magnetic field intensity. So it means these three are the same. By merging the Ampere circuit law and the Stokes theorem, we can say that I enclosed is equal to differential in the line integral of H dot dl and the surface integral of the curl of the magnetic field intensity. Okay, so now the application of the Stokes theorem. Okay, so let's suppose consider a conductor. This is a current carrying conductor. Consider a solid conductor. The direction of the current is shown in the figure. Okay, and the value is I. Let S be the area of the conductor. Okay, this is the area of the cross-sectional area of the conductor. So then the current density is given by J is equal to I over S. Okay, current density according to the definition, the current flowing through the surface, J is equal to I over S. Now assume a very small cross-sectional area. This is the small cross-sectional area of the conductor, and considering that the current in that small portion is di. Okay, in the full S the current is I. For the small the portion of the surface ds, we have the current also the small, the current will be di. So according to the definition of the current density, J is equal to I over ds. Now for the differential case, J will be equal to di over ds. It means di is equal to J ds. Okay, this is equation number 1. Now representing the current density as a vector quantity, so let its direction is along a unit vector A. J is equal to J, the direction of A. So similarly ds is also in the direction of A. Okay, so uh, assuming these two values, so according to equation number 1, we will get J dot ds is equal to J ds A dot A, means the dot product of two unit vectors that are in the same direction. So A dot A, that is equal to 1. So this is equation number 2. So comparing equation number 1 and 2, we will get this is equation number 1, this is equation number 2. Okay, so we will get I is equal to J dot ds. According to Stokes theorem, I is equal to this. So by comparing these two, we can see that I, and this is the integration, and this is the ds. So it means J is equal to the curl of the magnetic field intensity. Okay, so this relation is called the Maxwell second equation. Okay, so magnetic, now the magnetic flux and magnetic flux density. Okay, so consider an isolated north pole, which is practically not possible. Okay, So remember that if we have a magnet, and so it will always have two poles, north and south poles. If we cut it at the center, so it doesn't mean that we have separate south and north pole. No, we will have again the north and south pole in that small piece as well. If we cut it again at the center, so again we will have a small magnet having two poles, north and south again. So the practically isolated north pole or south pole is not possible. So but for uh, the, the the case of the repulsion and attraction, so let's suppose we will consider an isolated north pole. If we place another movable north pole in the vicinity of the field of this fixed north pole, so a repulsive force will be observed. There will be force of repulsion. Okay, the path followed by the isolated north pole is called the path of the line of the magnetic force. Okay, we will call it magnetic lines of force. Okay, just like electric lines of force. Okay, now this is the figure demonstration for the attraction and repulsion. Okay, now consider an open surface having the area S. So we need to find out the total lines of force passing through this surface area. This is the S, okay, and this is the differential ds, and the B is the magnetic uh, flux density, okay, and B is the normal to the surface. Okay, B is the magnetic flux density normal to the surface. So we can resolve the magnetic flux density into two components, Bn normal to the surface, as we know that in general B is equal to flux lines over area. The flux lines passing through a unit area is called magnetic flux density. So by this we can say that flux is equal to Ba. Okay. So from the figure we can see that uh, cos is equal to base by hypotenuse. So base is Bn. Okay, this is base. This is actually the hypotenuse, and this is the perpendicular. So base is Bn, hypotenuse is B. So cos theta is equal to Bn over B. By this we can say that Bn is equal to B cos theta. Now consider a very small portion of the open surface, that is ds. So ds is equal to in the direction of normal vector an. Okay, this is the normal unit vector of the surface. So d phi is the small portion of the flux, then d phi is equal to b and ds. D phi is equal to, according to this, bn is equal to b cos theta. So bn, replacing this value, we will get b cos theta ds. So as we have the cos component of the b, so by this we can write that there is a dot product between the b and ds. Okay, so b dot ds, this is the dot product between these two. If we expand this, we will get again b ds cos theta. So integrating both the sides to get the full flux lines, the phi is equal to b dot ds. Okay, this is the flux passing through the whole surface. Now the closed surface, consider a closed surface in the form of a sphere. Okay, and the previous one was the open surface. Now in this case we are considering the closed surface. So in order to find out the lines of the magnetic force passing through the closed surface in the outward direction, we consider a source inside the sphere. We have for example, we have a sphere. Okay, and in this sphere we are enclosing a source of the magnetic flux lines, that is the magnet. Okay, so the flux lines are coming out of the that closed surface, just like we have considered a closed surface in the Gaussian theorem, and that surface was called the Gaussian surface. So in this case we have a sphere, and the magnet is enclosed. In the Gaussian theorem, we have considered a charge enclosed in that, in the closed surface, but this is the case for the magnet. Hence, consider a bar magnet inside the sphere. The flux is coming out of that closed surface at one pole and enters the closed surface and the other coming out at the other, then net magnetic flux will be zero because the lines of the magnetic flux are continuous. Okay, so by the divergence theorem you will get phi is equal to the surface integral of b dot ds and the volume integral of divergence of b. Okay, so this is equal to 0. So again, either the volume integral is equal to 0 or the divergence of b is equal to 0. So as we know that this cannot be equal to 0 because volume is having some value. So we can see, we can say that the divergence of b, divergence dot, this is equal to 0. Okay, so divergence dot b is equal to 0, and this is called the Maxwell third equation. Okay, so first we have considered the open surface for the magnet, and then we have considered the closed surface for the magnet. Okay, so this was all about the course. So thank you for the moment.